welcome back to EE 386. This is going to be the lecture for class number 6. And in today's lecture, we're going to go through two major topics. First one is going to be the canonical forms, specifically the first order and second order canonical forms. We're going to look at the different parameters within the canonical forms, see how they affect our output, and then we're going to use the canonical forms to design controls. We'll do a few examples of that. The second topic is going to be more of the control design for the systems that include disturbances, and that'll be different types of disturbances, such as the ones I've listed here, things with, or systems rather, with a constant disturbance, a stepwise constant disturbance. Remember from last lecture, we denoted the almost everywhere when we made our assumptions with that, but we basically treated these the same. We'll go more into depth with that. And then also different types of polynomial disturbances as well. So let's get started. Okay, so canonical forms. So you'll remember we have mentioned a few times the ITAE tables. ITAE actually stands for integral of time weighted absolute error, just if you're wondering what that means. So there were two types of ITAE tables that we have looked at and that are uploaded to Canvas in the file section as well, just for your convenience. They're also in your book, no matter what version you have. So these would be the step input and then also the ramp input. And those are just the ones that we will use the most often. There are others as well, like sign input and such. And by the way, when we're working problems or you have a test problem, I would specify which one you should use if I tell you to use specifically ITAE. Also with the omega sub n, because that does appear throughout the table. Okay, so the first two rows in particular are the first and second order systems. So you'll notice that we have the S parameter to represent our system order. And then we have the omega sub n that appears in the different coefficients. So actually, we can take the row 1 and row 2, first and second order, and say that they are a specific subcase of our canonical forms. So let's show that. The canonical forms are represented here. First order, if we were to have a first order system like this, it would have a tau, or you might see this written as 1 over tau, as long as you're consistent. I tend to teach it with tau, just being the coefficient itself, but it can also be written as 1 over tau and that be the coefficient, as long as you're consistent, just in case you ever see this written the other way. As long as you're consistent, it's fine, just be consistent, okay? And the second order is, if we had a second order system here, the first coefficient is 2 times rho, this is a rho Greek letter, and the omega sub n, and then the omega sub n squared. Okay, so if we were to compare these here, for the case of our tau being our natural frequency in the first order, and the case of our rho being 0.7 in the second order, everything else being the same, then this would be the case of the optimal canonical form, okay? So ITAE will always represent the optimal, the best possible case, okay? So let's list those out. For the first order, and then for the second order. Okay, so I'm going to be writing this a lot, so I do want you to understand what I'm writing. It is just a Greek letter rho, as we said before. It kind of looks like a very curly P or S with a loop or something like that. But, you know, I'll write it like that most of the time. Okay. All right. So, let's look at how these different parameters affect our system. Okay, so let's start with the first order system. So in the first order case, we have, let's use that first order system right there, our canonical form. All right, so I do want to point out that tau is a time constant. So tau is kind of a representation of a time value. It is always going to be positive. It's designed this way. So if tau is always positive, and this is the form that we adhere to, the canonical form here, this is a positive sign right here, so we can look very quickly at our characteristic equation, and just solving for that root, we would see that we always have a negative tau system root, okay? So we're always over here in the left-hand plane and on the real axis as well. So we are assured of stability. So that is a stable system for that case. Okay, remember, left-hand plane's where we always want to be. That's where you want to place your controlled system roots. Over here, you want to design your gains to ensure that you are within that left-hand plane. Anything, even a single root, any roots over here in the right-hand plane would mean that you have an unstable system. So we don't want that. And if we have the power to design, we never want to do that. We never want to design it to be over here. Okay? All right, so adhering to a canonical form, designing our control to mimic the canonical form would be a good idea for stability. Okay, so let's look at an example of that. So, and again, we're just dealing with that first order canonical form right now. We'll go to the second one in a moment. Okay, so for the first order canonical form, all right, let's say that we have a system that looks like this. We can see already that that is an unstable system. To do that, let's just look at the system root. Actually, characteristic equation. Let's just do the characteristic equation real quick. Factoring it is very trivial. So, got that, and that means our system root is 2. So it's over here in the real axis in the right-hand plane. Okay, remember that's not where we don't want to be, so it is unstable. We could take it further and show our general solution and all of that. And we would solve for C with the initial conditions if we have them. Okay, so we can see that that expands with respect to time with whatever value C is. C is positive or C is negative. Okay, so we can see easily that it is unstable. Okay, so I want to design a control to stabilize this, and I want to adhere to the canonical form. So let's do that. First of all, the system's going to be stabilized, and then it's also going to adhere to the first order canonical form. Now let's say that I give you some tau to adhere to, a specific tau. I'm going to leave this arbitrary because that encompasses all cases of tau. And if you have a specific value after the fact, you can always insert it later. Okay, so here is our control. This is a first order system, and as we learned in our last 2 lectures, we want to design a control with a feedback, so we have access to that output. We're going to design our control to be with respect to the minimal order technique that we've been looking at before. So I don't want to include that y single dot variable. I just want to use the regular y. Just the output of the system is sufficient for this case. Okay, so we'll design it as a ky. Okay. All right, so let's plug that in and form our controlled system. This is the natural system. And our controlled system is going to be y dot minus 2y equals k times y. If we simplify this, we will get y dot plus a negative 2 minus k times y. Set that equal to 0. All right, so what we were referring to before as our equation star, we would compare this to our model system, okay? In this case, since we want to adhere to the first order canonical form, that response, we want our output to look like that. We want our system roots to look like those system roots. So that means that's going to be my model equation. Okay, so here's my model equation. I want to mimic that one. Okay, so you can see that we just want to compare, in order to design k, compare this coefficient with this coefficient. So I can make an equation, just like so, and let's solve for k. Does it matter that tau is arbitrary? Nope, not at all. Not at all for right now. So we'll get that negative tau, and then we will move over a negative 2. Okay, it's just a quick double check. If we reflect this, we get a negative tau. We subtract the 2 from over here, and we have it. Okay, so this would be our value of k in this case. If we were to plug k back into our original controlled equation, this one right here, this equation star, we plug this back in, and check it. We should have roots that look exactly like our canonical form. So we plug that back in. Okay, and then simplifying, we cancel out and we have tau times y. Okay, so that checks out. We have the exact same system roots as our canonical form in that case. So now, you've already done this amount of work. If I said, hey, make sure that you're using tau equal to 4, you would just plug in your 4 here. Or you would plug in your 4 here and get your k value. Okay, so pretty easy. So now, that applies to any tau. If I were to say, well, I want you to adhere to a much faster system response than the tau that we started out with. Let's say I give you an initial tau. This is tau. And now, in example 2, and this is kind of an exercise in listening to the directions and not getting confused, but knowing the terminology and being comfortable with that. But let's say now, we want to adhere to a tau that is 10 times larger. So that doesn't really imply that much work. The only thing that you could do, or that you would need to do really, is use your original design and just plug in this new tau. So now, tau equals 10 times this tau 0, okay? So now I'm just gonna plug in this value, so let's make that 10 times tau 0 minus 2, okay? So I just pulled from this equation, and let's call this equation pointy star, like the Yeah. From equation pointy star. The other star is kind of like an asterisk symbol, so I'm not sure what to call that one. But yeah, okay. So we plug that in and we should get the same kind of equation. We should get this y dot, and let's just plug that in real quick. 10 times tau 0 times y equals 0. Okay, and that should be the result. All right, so we have a tau that's 10 times larger. Well, let me back up and tell you why I might ask you something like this, or why we would ever want to do something like this. We were talking before about the system roots. Okay, we know that left-hand plane is good and right-hand plane is bad. Let me make it just a... Let's say that this is the, not so much the sad face, but the haha, I get to design a control face. How about that? Okay, so things are already done over here. No need to do any designing unless your control problem is to make things better. So we are actually in this area. Okay, this is the lambda that we start out with. Okay, so it's in the left-hand plane, everything's stable, everything's good. Now, if I make tau much larger, and we can examine this from the characteristic equation, characteristic equation initially was just our negative, let's see, made a slanted line, was negative tau. Okay, that was really the first tau that we started out with. Now, if we were to raise it by 10 tau, so we went from here to here, we've got this tau way out here. Okay, this is our, let's say our lambda 2. Okay, should have made that lambda 1, but anyway, so we've actually moved the system root further out in the left-hand plane. We were talking about this before a little bit, but just to repeat it, our system response is going to be better because we've done that. We have actually increased our quality of stability. Okay, so system roots that are further out in the left-hand plane are even better than just being in the left-hand plane. Okay, of course there's a cost, we've mentioned that before. The cost is higher control gains. And we can kind of see this with this example. So now, let's say that our tau 0 was just 1, okay? So we can see that our tau 0 would have been a negative, let's see, negative 12 in this case, whereas it would have been just a negative 3 in this case. So we did see an increase in control gain, okay? So higher control gains, and that can imply expense. Okay, so in general, for the way that we have learned this canonical form, the higher the value of tau, the faster the system response transient. Okay, so that transient, you may know this terminology already, but really that's just this distance right here, this area where we are reaching to 0, we're trying to settle, and this should go to 0. I meant to flatline that, but it's this area right here, okay? So how long it takes to reach 0. Okay, so if we have the higher value of tau, it would go much faster, as we saw in that plot that I drew first, but really the same thing here, okay? this, of course, was for the first order. So there's not a lot of variation for the first order. It's very easy to see what happens with changing this one parameter. Okay. All right, so let's talk now about the second order. All right, so this was for our second order system. Okay, so there's a couple things we can do with this. First of all, we want to look at the effect of the natural frequency. Remember, for the first order, our natural frequency was just the same as tau. Even if you looked at the ITAE optimized version, there really wasn't any difference. We had that row one up here, it just had the omega sub n, and here it was just tau. So really they were kind of the same thing. But here we have the ability to change these values. So we have omega sub n, and again, that's the natural frequency. And then we have this rho value that is called the damping coefficient. Or the damping factor. Okay, so these change your system response in a few different ways. Okay, so first of all, let's look at the effect, well, actually, let's find the system roots before we do anything else. Okay, so our characteristic equation will be a lambda squared plus 2 times rho omega sub n times lambda plus omega sub n squared. Okay. All right, so now what we want to do is we want to factor these guys. And actually, to find the system roots, what we could do is just use the quadratic equation. So let's do that. Okay, so here, lambda 1 and 2, there will be 2 of them in second order, equals, let's see, negative b, negative all of this, to rho times omega sub n plus or minus the square root of b squared, so all of this squared, minus 4 times a, which is 1, times c, which is omega sub n squared. Now all of that over 2a, which is 1. Okay. All right, so if we were to break this out and simplify it a little bit, we have, canceling those 2's, negative omega sub n and rho over here, plus or minus, and breaking this out, we're going to do a little bit of pre-simplification before we get our ultimate form for the roots. Okay, so I'm going to square each of these terms, and that's going to be 4 rho squared, so you can just go ahead and square each of the terms as long as they're multiplied together. That's the same thing. And 4 omega sub n squared. Okay. All right, so each of these have 4. We can pull that 4 out. Once it leaves the square root and is pulled out in the front, it becomes a 2, because 2 times 2 is 4. So let's go ahead and simplify that over here. Okay, so now we've got rho squared omega sub n squared minus omega sub n squared. Okay. All right, so we've got that omega sub n in both places. We can factor that out. All right, so I've got that omega sub n squared, and then I've got the rho squared minus 1. Okay, so I can go ahead and pull this guy out. Once it leaves the square root, it becomes just omega sub n, because the square root of something squared is itself. Okay, so is it possible to simplify this any further? Well, yes. The fact is, what we can do is take the case of any time that we have a value of something that's complex, rather. So if we factor that in, or rather factor the negative square root of 1 out. So let me just show you real quick. What if my rho value is something like a 0.7? Remember I said that 0.7 is the optimal value from our ITA chart? Well, if it's 0.7 and it gets squared, it's going to be less than 1, right? So this subtraction of 1 is going to leave us with a negative value. And so a square root of a negative value, that's going to give us a complex value, right? So we can go ahead and factor that out. Okay, so I'm going to write that j right there. And so the j is going to take care of the negative 1. It's also going to, since we factored out the negative 1, we are going to swap the values, just like so. Okay, you see how I did that? All right, so what we can do, we could factor out this omega sub n from the whole problem if we wanted to. I think this is good enough right here. So let's look at the plot of these guys on the complex plane. All right, so this is the real part. And this magnitude, aside from the j, all of this is the imaginary part. All right, so let's look at the real part first. It's negative, so it's going to be over in this region. And then we've got the rho value and the omega sub n value. Okay, so let's say that that distance right there is rho omega sub n. Okay. And then we're going to have two roots. Looks like we have a positive and then we have a negative. So let's look at the positive one first, because we know that they are going to come in a pair. Okay, so the imaginary distance up on this side of the axis right here is going to be the square root of 1 minus rho squared, and all of that is going to be multiplied by this omega sub n. Okay, so that's going to give us this distance right here. Okay, all right, so of course we're going to have a root that is made up of this distance in the imaginary axis and this distance on the real axis. So this is going to be, let's say this is lambda 1, and that's the positive root. We're going to have another one down here, the exact same distance, only it's negative. Okay, and that'll be our lambda 2. Okay, now we can look at this magnitude right here, and they describe this in your text, so you can find it in your textbook. I believe that it is in chapter 2 for sure, but I'll go ahead and list the page number when I make the Canvas announcement for this lecture. But anyway, if we were to find this distance right here, notice that we could use the Pythagorean Theorem to do that. And so we could take the real distance, that is the real axis magnitude. And consider that Pythagorean theorem, let's see, I almost wrote an R, so Pythagorean. Where if you are finding a distance here along the hypotenuse of a triangle, that is considered the distance C. So we really have an A, B, and a C here. And a squared plus b squared equals c squared. Okay, so that real distance squared plus the imaginary distance, that is the imaginary axis magnitude, and that squared equals the hypotenuse magnitude squared. Okay, so if we did that, we would get rho times omega sub n squared plus this right here, which was omega sub n square root of 1 minus rho squared, and then that should equal our hypotenuse distance squared. So we'll call that distance C. Okay. All right, so if we were to solve this, just squaring these terms, okay, and this square just relieves the square root right there. Let's go ahead and simplify this a little bit. We have that omega squared and omega sub n squared plus, and let's just distribute this, minus omega sub n rho squared. Okay, and then these cancel. Forgot to write the square there. There we go. And that equals omega sub n squared. So we know that that should equal c squared. So c equals omega sub n. So we've now discovered this distance right here. Okay. And likewise, we could also use the angle here and use your trigonomic formulas to discover that as well. Okay. So anytime there's like a right triangle like that, that's really handy. And you can follow along in your textbook, and I will leave the page numbers again in that announcement. And I'll probably go back and write them in these notes as well. But, so we can map out the roots. We are guaranteed, one of the main points of my doing this is to show you that we'll have a pair of roots. They will be complex, and then they will both be affected by this rho parameter and this omega sub n parameter. Okay, so that tells you a few things. They're complex. We're going to have harmonics. They're imaginary, they're left-hand plane oriented, so they are going to be stabilizing the system. We're going to be decaying to 0, okay? And that is dependent on rho being positive, okay? All right, so that leads me to talking about the valid range for rho. Okay, let's see, valid range. So we will normally talk about rho being between 0, it's something greater than 0, and it's usually something less than or equal to 1. So I'm going to put 1.0, okay? Because we do have decimals in here mostly, okay? We know that rho optimal equals 0.7. Now, the plots of, we're going to look at a couple different plots with varying values of rho. Now, if you remember the name of rho, the damping coefficient, you will expect that the damping is affected, essentially. Okay, so let's look at a few different variations. All right, so y of t in axis versus time. Okay, in this first plot, let's look at an optimal range. Okay, so the optimal plot of a system, let's just write it back out over here so we have something to reference. Okay, so if we're in the optimal situation and our rho is equal to 0.7, then the plot is going to look something like this. Okay, there are harmonics, nothing too severe, but we do reach 0 within a reasonable amount of time. Okay, we can predict where things happen adhering to this. So our system roots, everything is very well known in this situation. Nothing happens too quickly, and there's not a lot of variation, but we do reach 0 fairly quickly. Okay, and I'm just trying to describe what's happening with the plot here. Okay, all right, so let's say that we have a situation to compare by where rho is something small. Okay, a small value of rho, say, is something like a 0.1, 0.2, something like that. It's pretty small compared to the 0.7. Okay, so how is that going to affect everything? All right, before I plot this, let's just quickly refer back to this root plot, okay? So we can kind of see what's going to happen at this stage. All right, this term, and we're holding, by the way, for all these plots, we're holding the omega sub n constant. Omega sub n is not varying here. We'll come back to the omega sub n and see what happens when we change the value in a moment, but we need to hold one constant and vary the other here. Okay, so this gets really small, this real part, okay? And then this imaginary part right here, or this, the complex part of it, this is actually going to become smaller as well, okay? So what's happened is that we've gone from a situation of having root to now having a very small real part. So this has decreased dramatically, and maybe the complex part, let's see, draw that a little bit shorter as well. So we've got this kind of a situation here, okay? We've moved in that direction and we've moved in that direction, okay? So what's going to happen is that we are going to have a much larger amount of harmonics in here. They are going to decay, okay? And we're going to see that kind of behavior, okay? And actually, the smaller rho is, the more of these variations we're going to see, okay? All right, these are called ringing, okay, in just in terminology, okay? So there's more ringing with the smaller rho, okay? All right, so let's talk about now rho being pretty large. Let's say that that's about equal to 1.0, so our maximum, okay? Let's look back at our roots, okay? So rho is now very large again, omega sub n is constant. So our roots have moved now more in this direction. So they are further in the left-hand plane, so that part's good, right? And then they have also increased, let's see, we're looking at this equation right here. They have also increased in variation of complex or imaginary axis. So they've also moved out this way. So let's say our new roots are these with the darker axis out here. Okay. All right, so we should get a case that looks more like this. It is going to reach 0. it's going to have less of these harmonics involved. So actually, if we look at this right here, yeah, I'm sorry about that. This is actually going to be 0. So we actually don't have, since we chose 1, we're going to have 0 right here. We're not going to be moving out in the complex plane. So forget that. Sorry about that. Just drew it in the opposite way. So yes, we are moving further out in the left-hand plane, but we are moving, since we chose 1, these are actually going to be totally real. So they're going to be on the real axis. So we're going to have the dark x's right here, okay? Or the bold x's right there. So this is going to be the plot, okay? So this is for rho large, okay? So we're going to have a case of more ringing up here. We are going to have a case of a less ringing, less harmonics. But the bad part about this is that we are going to reach 0 in a longer time period. Okay, so yes, we did move our system roots further out on the left-hand plane, but when we were able to have a complex value, we were able to cross that 0 mark much sooner. Okay. All right, and in the settling time and all of that, we have to consider here our first 0 crossing occurs here. Now we do want to take into account the settling time, but it's going to be way out here before we finally reach within our desired delta of 0. Okay. All right, so this is, I usually just sum this up as saying this is the sluggish response. Okay, this is the optimal response. And then this is the overdamped response. Or I said overdamped, I meant underdamped. Okay, there we go. All right. So that's how rho will affect our system. Now let's look at what happens with omega n. Okay. So omega sub n varies here. Is it varies with I? I think it is. Yeah, that looks right. Oops. Varies here, and rho is held constant. Okay, so now we're going to look at how the frequency changes our plots. All right, so we really have, again, we can look at 3 cases. Let's keep it just a constant value to compare against, and then we'll make it very small and very large. Okay, so again, this axis is going to be y of t, cross here, cross x-axis, okay? And then we're going to have the case of omega sub n, let's just say nominal. All right, again, that one's just for comparing. And so omega sub n is, let's say, we'll do small on the very top one and large on the very bottom one. Okay. All right, so before I plot this, and actually let's go ahead and put the optimal one right in here. So before I plot these two, we want to talk about frequency versus time period, and that's really what's going to reveal the behavior. We can again cite the roots. We look back up here, so I'm going to increase in the negative magnitude, or rather I'm going to increase the magnitude along the real axis. If I increase the omega sub n, I'm also going to increase the imaginary magnitude. So what's going to happen is I increase omega sub n, well, I'm going to move this direction with my roots, and I'm also going to separate them further. Okay, and the opposite happens if I decrease omega sub n, okay? All right, so you can use that information to plot, and more simply, you can relate that frequency and time period have an inverse relationship. Okay, so you may have seen an equation similar to this before, where you have a frequency, maybe it was omega, maybe it was lowercase f before. So really, if you increase the frequency, you are decreasing the time period. Okay? If you do the inverse, you increase the time period, you are decreasing the frequency by this relationship. Okay? So we can have, actually, if we don't change, remember, we don't change rho for what we're talking about right now. What we're going to be doing, if we increase the frequency, we're going to be taking this graph and pretty much just squishing it. Don't think of it like that. And the same thing, or rather the opposite thing for increasing, sorry, I think I put my hands in the wrong place here, but increasing frequency decreases the time period. Okay, so we would be down here for squishing. Okay, and then we would be expanding for a smaller frequency. So it would look like this. So I'm going to try and make this y0, and we're going to try and say y0 again because we haven't changed any initial conditions. Okay, so it'll look like this right here for a larger frequency, and for a smaller frequency, expanded, just kind of like stretched out the graph. Okay, so visually you can see that effect. Okay, well, let's say that we have omega sub n here, and I'm not being too precise, as you can tell with my plots. I'm not marking anything on the axis specifically. If I were using MATLAB, I would do that. If I were calculating values out, then I would do that and go ahead and mark those. But let's say that we have 10 times, something like that, for example. And let's say we have like 1/10 of the omega sub n up here. Again, for example. Okay. So you can see those differences. Now let me mark a T0 down here. So let's say my T0 is there, and there. So you can kind of see the difference. Okay, so now let's do an example where we choose a control to create the, or make the system roots mimic the second order system. Okay. And I think this is going to be example 3. Okay. All right, so our problem statement is going to be something like, given a second order system, design a control to stabilize the system and make the system response mimic that of the second order canonical form okay. For this problem, I'm going to go ahead and give you some values. let's say omega sub n is equal to 2, and we're also, yeah, let's go ahead and pick a rho value. I'm going to say 0.4 for this. Okay, so basically, I've given you a specific system that I want you to design a control to make this other system look like the response of that one. Okay, we know that a second order canonical form system is going to be stable, provided that rho is positive. Okay, when I set the valid range up here, so I just want to give you a heads up. Valid range, let's just say for stability. It's not that rho can't be 10 here, it just typically isn't. But if I gave you a system and I ask you to analyze it with respect to the canonical form or something like that, and I made rho negative, well, I would expect for you to immediately know that a negative rho is going to have real roots over here in the real part, or the right-hand plane. So it's going to be in the positive real axis, and that's going to be unstable, okay? All right, so let me give you your system. Let's make something up. Let's say that this is like 4, let's make it negative 4, and yeah, that's fine. You can say, I make these up real time. And make that a 10, okay? All right, several ways of seeing that this is unstable. First one I just told you how to do, compare against the canonical form, and you can see, well, the rho is going to be negative. Rho is the only thing that could be negative. And valid range for stability, it's going to be positive, right? But we know that frequency is not going to be negative. If we look back there, hopefully this is clear when I make this comparison. Frequency and time are always going to be positive in this class. So the only other variable that could be negative here, if we were using this guide, would be rho. So rho is not time, it's not frequency, it's not something that absolutely has to be positive. It just has to be positive for stability. Okay. And then we always could find the system roots. We could always plot them. We could always use our usual methods as well. And necessary and sufficient conditions, of course, would also reveal that they fail for stability here. Okay, so now let's design our control. We can see that this is unstable through many methods. Okay, let's design our control. Okay, again, according to the minimal order technique that we've been using, we want to let u of t be something like this. k1y plus k2y dot. I don't need to include the y double dot because I can do the same amount of work with just these two terms if I choose my k1, k2 accordingly. So let's do that. Let's plug this in and form that controlled equation, simplify it, and get our equation star. Okay, set that equal to u of t. Okay, let's simplify that. Make that a little brighter. Okay, so we've simplified that as much as we can right now. That's now our equation star. this is the one that we want to use in comparison with whatever our model equation here, our model equation is, and that's going to set up our equations to design the K1, K2. Okay, here our model equation is going to be the second order canonical form with these specifications. Okay, model equation. Omega n is 2 and rho is equal to 0.4. Okay, so that gives us 2 times 0.4 times 2 y dot plus 2 squared y. Okay, so we compare these, and we have negative k2 minus 4 equals 4 times 4, so that's going to be 1.6 right there, 4 times 0.4 rather. Okay, and our second equation is going to be 10 minus k1 equal to 4, because 2 squared is 4, of course. All right, let's solve for k1 first. K1 is equal to 6, and K2 equal to 1.6 plus 4, and then we're going to subtract, or we're going to reflect that negative sign. There we go, 5.6. All right, so K1 equals 6. K2 equals negative 5.6, and those are our two gain values. All right, so let's go ahead and put those into our control and write out our control algorithm. So here, u of t is equal to 6y minus 5.6 y dot. Again, we have access to y dot, and you don't know anything else right now. That's all you know, having access to everything. That's fine. Okay, we have designed a complete control for this. We mimic the second order system. What we could do is go ahead and plug these in, see where our system roots end up, make sure that they're in the left-hand plane, if they're complex or not. We could do that. And then we could plot our y of t, and we should get something that kind of looks like that. It kind of has that behavior where it both decays, but it has harmonics in it. Okay, anything complex is going to have harmonics in it, by the way. It's going to have some kind of a sinusoidal response, and you can see that from the general equations, general solution equations. Okay, so what I'd like to do here is draw the math flow diagram in this case. So you remember how we did that at the end of last class, where we wanted to get the highest order derivative on one side, everything else on the other side, and then start working towards the left and towards the right in our diagram, in our drawing. Or, yeah, I actually just said the wrong directions, but I was pointing in the right direction, so hopefully that's not confusing. But anyway, let's do that. Let's have our natural system. Let's have our control equation visible. Okay, let's draw the math flow diagram for the complete system. Okay, if I say complete system, it should have the control. If I say controlled system, it should also have the control. If I say natural system, you don't have to bother substituting in the control. It would be everything up here. And if we had a disturbance, that would also be included. Disturbance is part of the natural system, if we have one. Okay, so our equation for the original system, the natural system, in this case, y dot dot minus 4, y dot plus 10y. And then we have our control signal right here. Okay, so let's get it in the form that we can work with. We have 4y dot minus 10y. Okay, this is good to go now. All right, so first thing I want to do is take this portion right here. This is going to be y double dot. Now I know that I'm going to want a y as an output, so I'm going to go ahead and do the integrators out here just to produce that signal. And that would make this y dot, since if it gets integrated once, it becomes y dot, okay? And again, we have y. Now let's not forget the initial conditions. They are part of the integrators. Okay. All right, now, so the problem is creating this y double dot signal. We have an equation telling us how to do that. So I have a 4 times y dot. I'm just going to add that right here. Let's draw our gain, which is a 4. That's our coefficient. And we'll draw off of this signal right here. Okay, the second term is this negative 10 times y. I have y right here. And I have 10. Okay, and I'm actually going to choose to subtract that here. I could also put a negative here if I wanted, but I have to choose one or the other. Okay, otherwise they cancel out. Okay, all right, so this is now our complete natural system. All right, so now I want to add in the control. I'm going to put an input right here and make that added. And this is going to be our u of t signal. Okay, remember when we design a control algorithm, we are feeding an input, a modified input into our system. Remember, we have our control. That goes into our process or plant, depending on what phrase you're using. And then we use that feedback from the output as one of the inputs to our control. We might also have a reference input. Okay, most of the time I will draw it with a summation right here, and this will be a negative feedback, and a reference input will just be added in if we have it, okay? And then that will be the input to our control, okay? But our control algorithm produces this u of t signal that is the input to our process. So we're modifying the input, not modifying the process, but modifying the input to that process to get a different output. Okay, so that's why I need to put that control signal as the input here. Go ahead and write that as y of t. Okay, so here's our signal right here, and it's already in the form that we want to work with. We have our end of our process of the control, u of t. That's our output of the control process or algorithm. All right, 6y. Okay, so I have access to y right here. I'm going to go ahead and draw it off of here. And I'm going to put 6 right here as a gain. So now I have 6y, and I'm going to need to add that to this next entry. Okay. All right, so now sometimes I probably could have planned this. I could go up this way to avoid a jump, but it's fine if you have a jump sometimes. Just like right here, I'm gonna have to jump that signal. And again, right here. Just make it very obvious. And I like to make these little jumps right here, just like that. So it's very obvious that those are not crossing, they're not junctioned. Okay, and we have a negative 5.6. I'm gonna do the same thing I did over here and make a negative on the summing junction. And our gain is going to be 5.6. Okay, this should look exactly like the Simulink. If you were to draw this up in Simulink, the shapes are going to be the same. Gains are triangles. Some summation blocks or circles. Initially, you can change the shape of them, but yeah, they start out looking this way. Okay. All right. And if it's not obvious where a signal is going, add in an arrow. And always add in arrows to your summing junctions as well. okay? All right, so we've got the math flow diagram right here. We can see the control part. We can see the process part. So this is really the control, and this is the process or plant or natural system, okay? Okay, so we've got all of that. Now, the other thing that I wanted to cover in this lecture was control design for systems with disturbances. So let's start that, and we will carry that over into the next lecture probably. All right, so control design for systems with disturbances. Okay, so we might have, actually let's refer back to this page a little bit more. We might have a disturbance of some known structure but unknown value. So I don't necessarily know the value of CW or CW1, CW2, anything like that. All I know is that it possibly varies in time and that it might have a structure that is similar to this, okay? It doesn't really matter what the values are in particular for the disturbance. Like, we don't really care right now what the coefficients here are. That doesn't really hurt us. What we're gonna do is design a control that will encompass any kind of structure like this, okay? All right, control design for systems with disturbances. Okay, I've said this before, but I'm gonna go ahead and say it one more time. I never ever want you to do this. Okay, what's wrong with this? Just answer in your head real quick. Okay, if you answered that I don't have access to that disturbance, I can't measure it, I don't know what the values are, you were absolutely correct, okay? Okay, so this is never okay. And inevitably, anytime I teach this course, I see somebody try to do this, or they might try to do this a few times because they forget. It's not okay to do this because you can't do this in reality. You can't just design a control for a rocket and think, oh, okay, well, I'll just put the wind right here. You can't rely on knowing what it's going to be ahead of time, okay? And I'm not counting a case where you have a sensor on your rocket and you are actively measuring the wind. I'm talking about a case where you are designing a control before that rocket's even in place to guide it. And you know, well, the wind's gonna be 15 miles per hour always, coming from the northeast direction. Like, you don't know that. So don't count on that, okay? All right, so cannot measure. Cannot put in control. Okay, and I'm gonna write a big no out here just in case somebody looks at the notes later and wants to do this. Don't do it. Okay, probably sounds really repetitive, but I want you to know that. Be very, very clear. We can never do that. Okay, well, now, there are cases, I'm just going to mention this, there are cases and more advanced control techniques, particularly in modern control, where you can estimate signals. If you are using an estimated signal, that is completely different from doing this. You've created something and it is your best guess based on other measurements in your system, and you are deducing the range that you think it falls into, and you are using that signal in your control. That's one of your signals. That is not the same as this. Those signals are usually denoted with some kind of a hat symbol, okay? So you may see this later, and particularly if you take the follow-on course to this, but this is something that is created by an observer technique, okay? We don't really go into this in this class, but I do want you to know that this exists. So it's not the same, and if you ever see something that is like a disturbance estimated signal, that is not the same as this, and that's completely fine to use. An estimated signal is your signal, you've created it, okay? All right, so what we're going to do is we're going to use integration techniques to cope with having a disturbance, okay? All right, so for example, let's just talk through an example, and then we will pinpoint the technique that we're using. Okay, so actually I should have written for example right there. So for example, we have a system, make it second order, and it'll look like this right here. We'll make it unstable. Okay, remember, disturbance is an input. So anything that's an input to our process, this is our process, the inputs go over here. So that's why we're putting our control over here. Okay, process and inputs. And then we gather our outputs out here, okay? And so these are going to be y dot, and so forth. These inputs are going to be u of t if we design a control. They're going to be the disturbance signal. They're going to be the reference signal if we have one, okay? All right, so we've got that right there. This is our situation. This is actually the natural system as well. No controls in place. Note that. That was our stipulation for having a natural system or not, if there was a control in place. The controlled system is the one with the control in it. Okay, so natural system. Okay, what do I do with this control? Well, I need a little bit of information. So for this particular example, I'm going to say that we have a situation where we know the structure of the disturbance. It is a CW1 plus a CW2 times T. So it's a ramp and bias, or a linear polynomial of first order. Okay, so it does that kind of a behavior right there. Okay, I might not necessarily know that it's positive, so I can say that it's also this case, also this case, and also this case. Okay, I don't know the value it starts at, and I don't know the value of the slope either. Okay, could be negative, could be positive, could start anywhere. Okay, and this is our plot of WT. All right, so what do we do? Well, the first thing I want to do is look at this disturbance, and I want to see how many derivatives I have to take of this to make it go to zero, or make it go to zero almost everywhere if it's stepwise. All right, in this case, WT dot is equal to CW2 just by itself. So this is not zero if we take a derivative. Okay, if we take a second derivative, again, we're just taking the derivative of the structure. So I didn't specify that this is stepwise, so I'm able to write zero. If it's stepwise, it's not zero. We'll do an example after with that. Okay, all right, so this number, here we have our zero, okay? This number of derivatives is important to us. That is the number of integrals I'm going to need to include in my control. Okay. So let's look at the control algorithm, how that's going to change. I think I did an example in last class where I didn't include the integral at all, and we plugged it in with the rocket and saw that it wasn't adequate enough we still had that disturbance. That's what's going to happen if I don't account for any integrals, okay? If you've got a disturbance, you're going to need at least one integral. If you have a disturbance that is more than a constant or stepwise constant, you're going to need multiple integrals. So if I am doing this correctly, my new control algorithm should be u of t equals our usual expected k1y. This is second order, so I need to include both a y term and a y dot term. So I've got that. That part we expect, we recognize that. This is the stability part. Okay, and I'm going to denote that as u sub s of t. And then we've also got this k3 integral of y of t dt. Okay, another big point, just like I pointed out this before, and I've done that at least twice now. Don't forget to include your dt terms whenever you have an integral. Okay, these two go together; they are one unit. That is the complete symbol for integration. Okay, and we'll also have a k4 double integral y of t dt, and then dt. Okay, dt for this first integral, dt for this second integral. Okay, and this is going to be the disturbance accommodating part. And I'm going to denote that as u sub w of t. Okay, you could also say u sub d. Sometimes I put a d here as well. Okay, so why do I need two integrals? Well, that should correspond with the number of derivatives here to achieve 0 for the first time in our disturbance. Okay, and again, we are not dealing with the actual disturbance signal. This is just, as much as I know about it, this is the structure. Okay, so I'm dealing with the structure only. Okay, so this is our new control algorithm. We will then take our system and form the controlled system, our equation star that we'd be dealing with before. Y dot dot plus 4y dot minus 5y equals, of course, we can't get rid of the disturbance, so it's one of the inputs, but we also have our control signal now. That's one of the inputs, and our control signal is right here. K1y, K2 y dot, K3 integral y dt, K4 double integral y dt, and dt. Okay, and this is all u of t. Okay, so now you plug in your control, form that controlled system. Okay, all right, so what do I do now? Because I've still got this. Well, I want to take the derivative of the system until I get rid of this. And then whatever is left over, I want to be able to stabilize and design my control gains to stabilize that system. Okay? All right, so let's do that. If I know from looking at this earlier, looking at the structure, I'm going to need to take the derivative twice. So let's do that. Okay, so it's only twice for this problem. Okay, this is not a rule that you take the derivative twice in every case. If I had a constant, and this may be obvious to you, and that's totally fine, but if I had just a constant, I'd only be dealing with one derivative. This would already be 0 at the first derivative. Okay, okay, so this is only for this problem. Okay. All right, why 4 dots? So 4 dots is kind of the point where you could do y 4. Anything above 4, I generally do that. I write the little number in the parentheses. And that's kind of the normal thing to do with papers and textbooks. Okay, so we've done this side completely. We know that second derivative of our disturbance is 0 in this case. Okay, and then we take the derivative of everything on this side. We have k1 y double dot plus k2 y triple dot plus k3 y single dot plus k4, and that's just going to be y. Okay, so now let's combine and we will form that equation star. Okay, and then we've got 4 minus k2 and then we've got a negative 5 minus k1 dot dot. Then we've got a minus k3 y single dot and a k4, and this actually should be subtracted as well because we moved it over, equals 0. So now, since we've got that equals 0 and everything's combined and simplified, this is our equation star. So that's the criteria for being equation star or not. And I totally didn't intend to keep using the symbol, but it's been so handy since we've been talking about all of this. So it's a good reference symbol, I think, just to keep referring to it as something. So anyway, what we want to do is get a model equation. So need a model equation. Okay, so the model equation is the thing that we want to mimic. It can be the ITAE row. If we had a 4th order canonical form, we could use that. I don't teach 4th order canonical forms, but you could also use root assignment if you wanted to do that. So let's say in this case that we'll just do ITAE because that's really easy. So I think that ITAE you do have the table on Canvas if you needed to find it. I'm gonna real quick flip in the book because I have lost my page. Okay. All right, here we are. 319 if you're following along in version 13, that is, and if not, you could always pull it up off Canvas because it's there in the files section. But yeah, so we have a 4th order system, so I'm going to need to use this 4th row right here. Let's write that out. So ITAE used here. So we have s to the 4th plus 2.1 omega sub n s cubed, 3.4 omega sub n squared s squared, plus 2.7 omega sub n cubed s plus the omega sub n to the 4th power. Okay, so there we go. All right, so and let's say that we wanted to use omega sub n equal to 1. Let's just do something easy. So then that reduces to 2.1 s cubed, 3.4 s squared, 2.7 s, and 1. Okay, so that's the evaluation bar at omega equals 0, omega sub n, and we got that right there. Okay, So now, from comparing this equation with our equation star right here, we can get what the values of k are. We should have 4 equations because we have 4 unknowns in here. All right, so form our equations. All right, so our first equation here is going to be 4 minus k2 equal 2.1. Second equation is going to be negative 5 minus k1 equal to 3.4. Third equation is going to be negative k3 equal to 2.7. So that one's already kind of given to us. We know that k3 is equal to negative 2.7. Okay. And then our last equation is that negative k4 equal 1. So that one's also kind of given to us. All right. So let's solve for these real quick. And we have 4 minus 2.1 is our k2 value. And then also k1 equals negative 5 minus 3.4. So here we've got negative 8.4, and here we've got 1.9. Okay, so we've got all of our k values from here. So u of t, let's go ahead and complete the problem and write out what our control algorithm ended up being. So k1y, so k1 times y, so plus k2 times y dot, so k2 times y dot, plus, and then we're going to have the integral y dt, and our value here was k3. So we have negative 2.7. And then finally, we have the k4, so that's going to be negative 1 times, and I could have just written the negative instead of a positive also, but that's fine, dt and dt. Okay, so this is our answer for our control. All right, so it was handy to go through one example and kind of go through the procedure to illustrate it first before we summed it up. So that's our completed control algorithm. And what we'll do is we'll outline the procedure and then we'll draw the math flow diagram, okay? All right, so the design procedure okay, so first of all, we examine our disturbance. Okay, examine that structure. So we get the number of derivatives needed to achieve 0 or 0 AE. Remember, that's the case where we have a stepwise signal as a part of our disturbance, okay? We can't guarantee 0 at all points in that case. All right, and then design a control algorithm. That includes let's call this M integrals. Okay, so for example, if we had M integrals that were needed, we would include y of t equals the stability portion and that portion, remember, was the minimal order design, to stabilize the undisturbed system. So if we didn't have that disturbance, that would be the portion that we needed to stabilize the rest of the system, like the y dot and y and the k values attached to those, okay? And then it will also include integral, like some ki value, y of t dt plus dot 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 plus m, the mth integral right there, y dt da, 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 dt, and that's the mth one of those. Okay, so we have a train of integrals, really. What I'm trying to show here is that you don't want to just have the stability portion and then that mth integral, like that right there. That's not adequate enough. And we could do an example where we plug in that and I show you the hole that is created in the equation. I could also just point it out. So, for example, here I knew that I needed a second order derivative to make that disturbance equal to 0. If I just stuck in that and I'd left out this right here, I would not have control over, let's see, I wouldn't have control over, let's see, our equation star, this term right here. This would be the one that was lost, this K3, all of that. So it's possible that I could have an unstable case in there for some given set of initial conditions. And I want to avoid that. I want to cover all initial condition sets in every control that I design. I don't want to just narrow it down, okay? I want it to work as often as possible, okay? All right, so yeah, that's why you have to start with the single integral and build it all the way up to the nth one, and that is all part of your control. So this is the disturbance accommodation part. Okay, all right, and then you will plug in the control. To the system and form the controlled equation. Okay, and that is your y double dot, whatever, however many, whatever system order you are, equals the w of t plus the u of t. Okay, that's this equation right here. All right, after you do that, you're going to take m derivatives. Okay, as a side effect of that, w of t to the mth derivative should equal 0 or 0 AE. Okay, if it has a stepwise component. Okay, and then you want to simplify, form the equation star, and then you will compare to your chosen model system. And solve for all of your k sub I or g sub I, whatever variable you are using. Again, I tend to stay with k's or g's, but you might have chosen other ones. We just had a list of variables you should stay out of, like s's, that'll get really confusing, or y's, so just adhere to that. Okay, but that's your general design procedure, and that'll cover any kind of disturbance that was in my list. So there were disturbances that are not in my list. These are polynomial type. Okay, so what about those? Well, actually there's two cases. what about disturbances that aren't polynomial type? That should have been an R. I promise I can spell, despite the fact that I've left out letters a few times. Disturbances that aren't polynomial. Or times when the disturbance structure isn't known. Okay, I really love to give this as a test question because it requires you to think about it. And I might do that at some point, so I'm going to be careful what I write down. So if you have a case where your disturbance does not fall within this list, well, it's not exactly that you're out of luck, but we don't have a linear in time design procedure to cover that. You might have, let's say, a nonlinear type of disturbance, or you might not even know that it's nonlinear if you don't even know the structure. So in that case, it's best to just do the best you can. And I know that sounds open-ended, but there are cases where things are so unknown that you actually just can't use a technique that we've covered. Remember, we are in, this. If we look in this bubble, this goes back to the first class lecture, all the systems that can ever exist. So it's a very, very big bubble. And then they're non-linear. All of them pretty much are non-linear. The ones that are linear are a subset of the non-linear. So just like we were talking about the canonical forms, and that is that ITAE is a subset of those canonical forms that are optimized, same thing here, where the linear is a subset of all the non-linear. Okay, and then we are specifically looking at things that are actually very, very tiny subset of LTI, linear time invariant systems, where my coefficients aren't really varying with time, or they are, but it's enough to neglect. Okay, so we're out here, and so some of the techniques that we, actually we don't have techniques to solve for a few of the disturbance cases. So it's kind of a question where it is up to you as the designer with your specific system, using your knowledge at that time to make the best decision as possible. Dr. Johnson had this really good question that I remember, where it was, if you are running a race and you don't know where the finish line is, it could be anywhere, you have no information about it, how do you run that race? How do you pace yourself? And so it's really up to you to answer that with your best guess, your knowledge of the system, and your perspective, okay? So, for example, let's say that we had just a very simple system right here. Let me show you what I'm talking about. So my disturbance, and let's say I design a control right here, okay? So let's say I have something like e to the alpha t, something like that. So it's an exponential. I try and take the derivative of that. Oh, should have started the equation off properly. There, just like that. That is alpha t, of course. All right. So have we decayed things? No, we are making them worse, right? Do it again, same kind of thing. Okay, I can take in derivatives of this disturbance structure, and it is not going to matter. I am not going to be able to decay this, right? We know that from calculus, from math, from, basic common sense. This is not going to decay. So have I really learned a technique to talk about that, or to try and discover it? No, not really. in this kind of case, you're going to have to use something like an observer signal where you kind of try to reconstruct this. And again, that's not one of our techniques in this class, but it is interesting to think about. I want you to be aware there are cases that we are not covering, okay? So something like a built estimated signal, something like that. Maybe if I can do that, maybe that would work, and I could put that in my control algorithm. So think about that. How to design U of T. All right. Maybe there is a case where I have enough knowledge of the system where I know that a disturbance that's significant enough to impact my output is pretty unlikely, or is only likely to occur in certain cases. And maybe I can narrow down my control algorithm in that way. So there's different things you can do, but again, there's not a one direct path like there is for the polynomial type disturbances that we've talked about. Okay, so that'll go ahead and conclude class number 6, and I'll see you again in class number 7, and we're going to go through more disturbance examples, and then we're also going to start talking about the design with the error and things that are beyond just simple stability. Okay, so I hope you enjoyed this, and I'll see you again next time.